Okay, so let's start. So 6.3 is anti-differentiation by parts. So we use this when our integrand is a product of values instead of the chain rule occurring. So in the previous section, what was happening is that we may have had two different quantities, but one quantity only existed because if we took the antiderivative and then derived that, the chain rule would happen. I'm just going to read a comment real quick. Okay, that sounds good to who just wrote me that. So I just did an example of what a problem would have looked like if it were to be the chain rule. So here I have the integral of cosine of x times secant squared of sine x dx. Now this is a pretty intense integrand. There's a lot of trig functions in here. And what I had recommended that people do for these problems is to establish their u value and then to see if the derivative of u existed somewhere in their integral. So taking a look, if I were to make the sine of x u, I know the derivative of sine is cosine. So I want to think to myself that does that chain rule exist somewhere in here? And I see that yes, it does. So I know that this isn't the product of cosine and the secant squared of sine x. This was the byproduct of the chain rule. And so just to write it out with our notations, I said capital F of x is equal to, and if we were to take the u substitution, and if I were to get rid of the sine of x and replace it with the quantity of u, and I were to replace the cosine of x with my u prime, so then that would be right in there as u prime. And I were to take the antiderivative, what I would see is that the antiderivative of secant squared, meaning what was that position function, would have been tangent. And so to work backwards, if I were to take the derivative of tangent, I would get secant squared. So you can see on how it relates with each other. And a lot of you did very, very well with this, but always add the plus c at the end of an indefinite integral because we're not evaluating it. And if we were to take the antiderivative of 0, it could have been any constant imaginable. And there's no way of knowing because the derivative of every constant is 0. So even though there is no constant here, it could have been any constant to begin with. And then just to finish it off, I'm going to replace my u value, again using substitution, with the sine of x. And then you can always double check your work by then just taking the derivative of the function that you just found. So taking the derivative of tangent sine x plus c, well, the derivative of c is 0, so it will go away. Here, the derivative of tangent was secant squared sine x, but then I have to multiply by the chain rule, so the derivative of sine x is cosine x. And so I can see that by taking the derivative of my antiderivative, I was left with my original integrand of cosine x secant squared of sine x. So the last section, that was in a nutshell how we were doing these problems. We were trying to find the antiderivative just to take the derivative and bring us back to where we had started. So that was a good way to double check our work. So that was an example of the previous section. Now, an example of the integration by parts would be something like this one here. We have the integral of x times the cosine of x. This is not the chain rule, because if I take the antiderivative of the cosine of x, that would give me simply sine of x. And if I take the derivative of sine of x to bring me back down to the integral stage, I would have cosine x. Nowhere in that process does an x magically appear. So that means that this x must have existed through the product of something else. So to derive my equation that I'm going to use, I am going to start off with the product rule. So originally, to take the derivative of the product of two values, I would have done the first times the derivative of the second plus the second times the derivative of the first. That is the product rule that we've been using since chapter 3 with, I think it was like the second or third rule on that sheet. So that's step 1. Now, step 2, if I go ahead and I integrate both sides. So I'm going to take the integral of the derivative of uv dx equals the integral of uv prime dx plus the integral of v u prime dx. So I'm just taking the integral of each quantity. Now, this integral of a derivative is going to cancel out because that's just saying take the antiderivative and then derive it. And that's going to give me where I started. So I can conclude that this quantity here is just going to be uv. So the integral of the derivative, that cancels out, and I'm just left with uv. Now over here, these quantities don't cancel out, so they stay the same. Now what I have here in my original problem is I have the integral of two quantities being multiplied together. Well, where I'm at here is I have two options for that integral. Either it's going to be my u value times the derivative of my v value, or it's my v value times the derivative of my u value. So that means that this x could be my u, my original u function, and that means that cosine is the derivative of my original v function. Or maybe cosine is my original function and x is the derivative of my original v function. So I have two choices here to make. Now I'm just going to do what the book had done, and they decided just to subtract this integral instead of that one. The reason why is that usually the first term is the first function and the second term is the derivative of the second function, usually, but not every time. And it's important to know that you can switch which is the u and which is the v prime based off of your preference. 99% of the time, one will be easier than the other. So once you try it one way, if it starts to get too complicated, or maybe you realize it's impossible, you want to switch your values and try it again. And so then my fourth and final step leads me to the formula that we're going to be using for integration by parts. And that is that if you are given some integral comprised of an original function and the derivative of a second original function in terms of x, it is equal to this formula right here. So you can take the original function times the other original function minus the integral of the second original function times the derivative of the first. And then I just kind of explained in words that this means that in our integrand, we have an original function, we have a derivative of another function. In step 3, we were free to subtract either quantity, so that means that we're able to assign the two values to either the u and the v prime, or the v and the u prime. And we usually try to make the u the easiest to differentiate, because once we have the u and the v prime, we're going to take the derivative of u and the antiderivative of v prime. So we're going to have 4 values, and they will all be found based off of our original integrand. Now in the next slide, I am going to go ahead and use this formula, the integration by parts, or anti-differentiation by parts, to evaluate this integral. But for those that are writing down, I'll give you a moment to keep on writing before I move to the next slide. And again, this PDF is already in the classroom. All right. Is anyone still writing? Okay. So here is my integral, and I want to figure out what would be a good u value and what would be a good v prime value. So I said that it's usually useful to make the first value u. So I'm going to just say that if this is x, then therefore this must be the cosine of x. So now that I have a u value established and a v prime value established, I am going to take the derivative of my u value, and I'm going to take the antiderivative of my v prime value. So the derivative of x is 1, and the antiderivative of cosine would be the sine of x, meaning the derivative of sine is cosine, the derivative of x is 1, the antiderivative of 1 is x, the antiderivative of cosine is sine. So now what I've done is I have my u value, which will go here. I have my u prime value, which will go here. I have my v value, which will go here and here. Notice how I'm not using the v prime, which makes sense because if we're doing the original function, we're going to be working with the u's and v's, not necessarily the v prime. And so now I'm going to go ahead and plug these values in. So my u value is x. My v value is the sine of x minus the integral of my v value times u prime dx. And now I'm going to simplify. What is the antiderivative of sine? Well, the antiderivative of sine would have been negative cosine because the derivative of cosine is negative sine. And so if I want the antiderivative of positive sine, it would have to be negative cosine. And now that I've gotten rid of my integral, I'm going to write plus c. And so x sine of x plus the cosine of x plus c is the antiderivative of the integral of x times the cosine of x dx. Give people a moment that are still writing down. And does anybody have any questions with the process? And again, you want to establish a u and a v prime. Once you do that, you can take the derivative, you can take the antiderivative, and then it's simply plugging it into the formula and then simplifying until that integral goes away. Okay. Then x natural log of x. So again, we are free to do this any way that we'd like. Now, let's say I try to reverse this. So instead of making the x my u value, what if I did this? Now, if I would have done that, the first thing I'd want to do is figure out what is the derivative of the natural log of x. Now, if I wanted to do that, the natural log of x is 1 over x. And the antiderivative of x would be 1/2 x squared. So that works out. Well, what if I did it the first way? So I'm just setting this up two different ways. So that's option one. And what if I made that x and that the natural log of x? Well, the derivative of x is 1, and the antiderivative of the natural log of x, well, I would go ahead and look, and I'm looking at my formula sheet, and I'm looking for the integral of the natural log of x. We have a problem. There is no antiderivative for the natural log of x. We can't do it. So therefore, there is only one way to set up this problem, because this situation right here is not possible. We don't have the antiderivative of the natural log of x. We only have the derivative of the natural log of x. So I can't do it this way because I am missing a piece of information. So even though we are free to set it up either way, one way works, the other way does not. The smartboard keeps, whoops, defaulting, back to sharing. Okay, so now I'm going to use the u, v minus the integral of v u prime dx. So when I plug in, I would have the natural log of x times x squared over 2 minus the integral of my v value of 1/2 x squared times my u prime, which is 1 over x. And so what I did there is I just simplified this quantity, and it simplifies out to 1/2 x dx. So that 1 over x and the 1/2 x squared eventually simplify. And so now if I take the integral of this quantity, the antiderivative of 1/2 x, well, I know it's going to be x squared. And again, I have to think to myself, what would be the coefficient that would be in front? Well, if I am going to be bringing down the 2, and I would have 2x, what would have to be there in order to have 1/2 x? I would want a 1/4 in front of it. Because again, if I take the derivative of this 1/4 x squared, its result should have been my integrand. And if I bring down the 2, I get 2/4 or 1/2. And if I subtract 1, I get 1. So I do get 1/2 x. The shortcut to this is that whatever you're multiplying by, divide your previous coefficient by that, and then you'll get what you want. So since I know I'm multiplying by 2, if I divide the 1/2 by 2, I get 1/4. And then the last thing we need to throw in there is the plus c, because we need to account for any constant that would have been there that would have gone away when we take the derivative. So this function here, if you were to take the derivative of it, you would result in our original value. Pulling up the chat. Does anybody have any questions with that problem? It was a little different, but same general process. Okay, I have just one more example for you guys, and that is when there is a repeated integration by parts. So we're going to have to do the formula twice. So I'm looking at the x squared, I'm looking at the e to the x, and I want to decide which one should be my u and which one should be my v. Now, just so you know, it's this problem that the tabular integration is going to make a lot quicker. All right, so in case people can't see, Will is asking if he is the only one whose screen is totally blank. And everyone else seems to be able to see. Will, maybe try leaving the Zoom and coming back in. Okay, I'll wait for you to do that.
Nah, sorry, don't worry.
How could I not worry? That's right. I guess there'll be the recording, so you can always watch that too. All right, so with this one, the u and the v is going to be not too bad. So the u, if it were to be x squared, the derivative of x squared is going to be 2x. And then with the v prime, if I made it e to the x, the antiderivative of e to the x is just e to the x. So now I have my u's, my v's, my u primes, and my v primes. And so I'm going to plug it into the formula. Again, uv minus the integral of v u prime dx. So my u value is x squared. My v value is e to the x minus the integral of e to the x times 2x dx. So this one is good, but we now need to get rid of this integrand, this integral. Now, unfortunately, I am not seeing the chain rule because that means that there would had to have been a 2 in there. Instead, there's a 2x, which disrupts everything. So that means that I have another integration by parts that I would have to do, just using this second term. So I'm going to have to set it up again. My u value, I'm going to make 2x. My u prime, I'm going to make 2. And then my v prime, I'll make e to the x. And so my v is also e to the x. Now I'm going to rewrite this first term so I don't lose track of it. I'm going to put this next integration by parts in parentheses. So I remember that that negative has to be distributed. The two biggest issues that happen is sometimes people forget this first term. The second biggest issue is people forget to distribute the negative. All right, so u times v minus the integral of v times u prime. Now again, our constant multiple rule of integration says that we can take this constant out, move it in front. So what I appear to be having is this quantity here, and the antiderivative of e to the x is e to the x. So this lovely quantity is the antiderivative of the problem we started with. Rather nonsensical. We're just using the straight algebra of it. This makes a little bit more sense in future sections when we talk about logistic growth and exponential decay, and we get to use it a little more in the applications, but unfortunately we ran out of time. But this would be an example of when we'd have to do the integration by parts twice. Now you'll know that you'll need to do it because in our previous examples, if we take a look, this one had a linear term we were multiplying by. This one had a linear term we were multiplying by. And in this problem, we had a quadratic. Now, can you imagine what would have happened if we had a cubic function? That means we would have had to have done the anti-differentiation by parts once, done it twice to get it down to a quadratic, and done it a third time to get it down to the linear, which would have resulted in a constant. So the higher the degree of this first term is, that tells you how many times you're gonna have to do the integration by parts. So if I gave you something like 1/6 x to the 6 e to the x, you're gonna have to do the integration by parts 6 times. Now that obviously gets extremely tedious. That's where tabular integration comes in and speeds this process up. That's what we'll be doing. We'll do that on Thursday. We'll still keep that as the schedule because tomorrow is going to be for review work. So now that we're done with these notes, I'm going to go ahead and stop the recording.